Stepping away from that, let's get into the actual thought process, the scientific method. The scientific method is a process used to explore thoughts, events, or phenomena in science and other areas. This process will go into some detail and we'll talk about each of the steps involved. And it's a very methodical thing. It's very planned and thought out in order to know that we're getting, quote, the right answer, so to speak. When we're using the scientific method, we're focused on empirical knowledge, which is based on the experience and observations that are A, rational, B, testable, C, repeatable, and D, self-correcting. So we need to have rational thought. Things need to be logical. It needs to be testable because science being that process, we need to be able to put something to the test to get some sort of result. Those tests need to be repeatable, so someone else should be able to step in, do the same experiment or the same process that you did, and come up with similar, if not the same results. And we need to be self-correcting. Sometimes the things that we think are happening isn't really the truth, and that's okay, but we need to self-correct, meaning we need to be willing to accept the evidence that we have, and if that is conflicting with something we thought was going on, then we need to be willing to accept new information. So here we see our circle of scientific thinking, and in general, we start with an observation up at the top. An observation is just something that you have taken in about the world around you. And usually when we think of observations, we think visual, but it can be many things. It could be visual, it could be something auditory, it could be something tactile, based on touch. It could be some sort of data that we see that was collected from other experiments. There's a lot of things that would count as an observation. From there, we've seen something, we've collected something, we have some sort of data that we noticed a pattern or a trend in, we have some sort of observation, and now we want to give some sort of explanation behind what's causing that or what's possibly explaining the phenomenon that we saw in our observation. This is what we call the hypothesis. It's just a proposed explanation. Think of it kind of like an educated guess. Based on the observation we see and based on our previous knowledge, this is what we think might be happening or causing or explaining the phenomenon that we see happening in our observation. Unfortunately, for a lot of people, this is where they stop. But as scientists, we can't stop here. We need to take that hypothesis and put it to the test. So we have our hypothesis, our proposed explanation, our kind of educated guess of what we think is happening or why we think something's happening. And we form a prediction. Our prediction is something that is testable. And since it's testable, we then go on and put it to the test. We conduct our experiment. After we've conducted our experiment, we've gathered our data, we can then look at the data and then draw some sort of logical conclusion from that data. It's possible that our data and our conclusion supports our original hypothesis, but on some occasions, our conclusion doesn't support our hypothesis. Both answers are okay. We don't always have to get support for our hypothesis. Getting a conclusion that doesn't support it is still good science and still an answer. Now, in this picture, we see it going in a loop, into a circle. But we notice there's a couple arrows that are kind of branching off. This process is not necessarily linear. Now, in general, when you get started, you follow this process, but sometimes we end up having to jump around a little bit. Maybe we draw a conclusion that doesn't match our hypothesis and we have to revise our hypothesis and test it again in another way. That's okay. So for the sake of this course, you'll want to know these steps in the order they're being presented here: observation, hypothesis, prediction, experiment, and conclusion. But do keep in mind that this isn't a linear process, and so sometimes we can end up going from one step and skipping something, or moving forward, or going backwards if it's necessary. So let's get into a little more detail. Like I said, we're making observations, we're looking for some sort of pattern or some sort of cause and effect relationship, or at least something that seems to have a cause and effect relationship. Like I mentioned, this can be visual, it can be something with other senses like touch or taste or hearing, it can be patterns we see in numbers, in data that we've already gotten from someone else or from a previous experiment. There's many ways to make an observation. That hypothesis is our proposed explanation. So the hypothesis is a statement, not a question. So for example, if I notice in my garden that my plants who received fertilizer seem to be growing faster or taller than the plants that didn't receive fertilizer, my hypothesis could be that fertilizer causes plants to grow more or grow faster. That's a statement. But like I said, we can't stop there. That's where a lot of people get hung up. They stop with the explanation they come up in their head, but they never put it to the test. We're moving forward with that. Now, it's also possible that you have more than one hypothesis for the same observation. One of those extra hypotheses you might have is the null hypothesis. The null hypothesis says there's no relationship between the two things. So sometimes it's called the alternate or the alternative hypothesis, but in general, I usually hear it just called the null hypothesis. It doesn't mean there's a negative relationship though. So let's use the same example of the plants. My observation is that I noticed that the plants with the fertilizer are growing faster than the plants without the fertilizer. My original hypothesis was that fertilizer will positively affect plant growth. My null hypothesis would be that fertilizer has no effect on plant growth, not that it hurts plant growth. So it doesn't mean it has to be the negative kind of opposite. It just means that, hey, I'm seeing these plants grow more in fertilizer versus no fertilizer, but the null hypothesis is that fertilizer is not causing that change. Something else is. So again, you can have multiple hypotheses, like your original one you came up with, like fertilizer causes the plants to grow more, versus the null hypothesis, which just says the fertilizer has no effect. And you might have more than just those ones as well. That's okay. Once we have our hypothesis, we can make a testable prediction about the situation. These are commonly if-then statements. They don't have to be in that format, but that's the easiest format to identify and to write for ourselves. So we want to propose a situation that will give a particular outcome if our hypothesis is true, but a different outcome if the hypothesis is not. So if the hypothesis is true, then a particular situation will support my hypothesis. If this hypothesis is not true, a different situation will support my hypothesis. So if we're using our plant one again, we could say, if fertilizer positively affects plant growth, then plants that had no fertilizer previously and that get fertilizer added will experience faster growth. Or something like, if fertilizer positively affects plant growth, then plants that receive fertilizer will grow more than plants that don't receive fertilizer. We can put those to the test. We can have plants that have no fertilizer and plants that have fertilizer added, and then measure their growth over time. That's something we can actually conduct and test for. So that ties us into the next part, conducting an experiment. And that'll allow us to collect data to tell us if our hypothesis is better than the others. Keep in mind, we're not saying that the hypothesis is necessarily true. There's a reason behind that. As scientists, we're actually not big fans of the word prove. We prefer words like support. Simply because someone else could come along conducting other experiments in the same fashion or in the same kind of realm and find data that contradicts what we found. Well, who's right then? So we're really looking at a collective of evidence and then providing language that will say it supports this or it doesn't support this or fails to support this. So we conducted an experiment, right? We grew some plants that had fertilizer, we grew some plants that had no fertilizer. But once we've conducted that experiment, we have results that we can analyze, we look at the data, and then we can draw a conclusion based on that data, looking for a pattern or some sort of relationship that provides us the evidence of whether or not our hypothesis is supported. Again, if our results don't support our hypothesis, that doesn't make the experiment wrong or bad. It just says that, hey, your hypothesis didn't have the support from your experiment. We need to go back to our hypothesis list and revise it, and then possibly conduct new experiments. Sometimes we learn more from the incorrect hypothesis than the correct one. It's okay to make mistakes and change your mind. I'm going to tell you a little story about this. Now, back when I was in undergrad, I worked in a disease ecology lab, and we conducted experiments on frogs and toads and salamanders. For one particular experiment, we were exposing some toads to a fungal infection. We knew that this fungus was infective, we knew that it was causing disease, but we didn't know if it would cause disease in this particular species. So that's what the experiment was for, to find out how infective it was with these toads. So we came up with our hypothesis list, and we came up with our predictions, and we sat down to create our experiment. Well, we were having trouble because no one was getting infected, even after we exposed them twice. So we were thinking at first, well, maybe our hypotheses are not supported. We went back, we looked through everything, we looked at the experimental setup, and we found out something very new and something we didn't know before. The moss that we were using inside the little containers containing the toads was actually antifungal, and we did not know that. That was new, awesome information that we got that otherwise we would never found out if we didn't make a mistake. Once we removed the moss and put a different substrate inside the toads' cages, then the infections started ramping up in high numbers. We then had a new experiment to conduct off the side where we could look at this moss and see what kind of antifungal properties they had. So that was something where we made a basic mistake that we didn't necessarily think of or didn't know enough information to be able to avoid. And we ended up being able to create more questions and find more answers because of it. A lot of mistakes have led to some really cool discoveries in science. So don't think of it as you have to find data that supports your original hypothesis. Sometimes the best answers or the best thing that can happen is that you get it completely wrong. All right, moving on to the next one, we are going to talk about theory. Now, the way we use the word theory when we're speaking colloquially or casually, like our everyday language, theory is like an idea or a prediction. It's kind of closer to our hypothesis prediction area. And like I said, that's where a lot of people stop when they're using something like the scientific method. They don't follow all the way through. They get to the hypothesis, they come up with their own explanation, and they stop there. And so a lot of times we use the word theory when talking about that, when we're just speaking with our friends or family about regular everyday stuff. But we want to make a distinction because the word theory in science carries a lot more weight. It's a heavier term in science. A scientific theory is an explanation for natural phenomena and has to meet the following criteria. A, it's supported by lots of evidence. We mean lots of evidence. B, it's repeatedly tested by multiple people. C, it's accepted by the scientific community as a whole. And D, it is very unlikely to be contradicted. That's a very different definition from what our casual theory definition is. Let's think about it. If you're sitting down with your friends and you finished watching Game of Thrones and you were trying to talk about what you thought was going to happen in the next episode, you might say something like, my theory is that character X is going to die in the next episode. That's totally fine when you're just speaking with your friends, but a better way to say it would be, My idea or my prediction is that character X will die in the next episode. We wouldn't use that kind of blasé or sort of casual way to approach a theory. Let's talk about a very big theory in biology, the theory of evolution, or the cell theory, or germ theory. All of these that I've listed are supported by lots of evidence. And when we say lots, we mean a ton. We're talking about people's entire scientific careers being wrapped around the idea or the concept of creating experiments and collecting evidence that supports these theories. So we're talking about years, decades, sometimes even more of collecting data and collecting evidence that supports that particular concept. It's been repeatedly tested by multiple people. Like I said, people's entire careers are wrapped around collecting that evidence. So multiple people from all over the world have tested this particular concept over and over and over again. And that in general, we've found evidence that supports that idea and doesn't go against it. So it's unlikely to be contradicted. And then lastly, because of all this, it's generally accepted by the scientific community. Yes, on occasion you will find some rogue scientist who for some reason doesn't necessarily want to go with the crowd. However, scientific theories are generally accepted by the entire scientific community worldwide. It doesn't mean it's 100% consensus, but it's extremely high, and anyone who contradicts that is most definitely an outlier. So make sure you know the difference between those terms, because that is something, and we'll go into it when we get to a later unit, but that is something that you will see come up, where people will say, well, something like the theory of evolution is just a theory. Putting the word just in it downplays it significantly and points out that the person doesn't know the difference between the casual use of the word theory and the scientific version. Make sure you know the difference, and make sure you know what the scientific version of the word theory really stands for. Now, I mentioned this earlier, but we're going to go into it again. In science, we try to avoid the word prove or any sort of derivation of it, because if we say prove, it makes it sound like we can never revise it, that there's nothing that can ever change that end result or that hypothesis. But that's not necessarily true. We learn new information all the time, and sometimes that new information leads to us having to change previously held beliefs or previously held hypotheses. So instead, we like to say that something is supported by the evidence. Or if it's not, then we say it's not supported, or that our evidence fails to support our hypothesis. But it's generally wrapped around the word support over prove. And again, that's because science is changing. This is because we're finding new information. More people are conducting research. Better technology allows us to fine-tune experiments and collect data that we weren't able to collect before. Think about it. Before a microscope, how would you know that there was even something like a microscopic little cell in existence? But with that technology came new ideas and new evidence that changed our perception and changed how we viewed the natural world. So we want to think about how much research is being done, what it's being done on, and how technology can affect what evidence we're able to collect and what we're able to support or not support. But all in all, science is fluid, it's changing, and you have to be open to new information and new ideas if you want to be a scientist.